This is session number 8, and we'll cover duct run design. There are two types of duct runs that we use, and that is power duct runs and control duct runs. Usually 2-inch conduit is used for the control duct runs, and 4 to 5-inch conduit is used for the power duct runs. The type that we'll talk a little bit about tonight is power duct runs, since most of the design factors will apply to both types. Duct runs are used where it is desirable or necessary to locate power cables underground. The largest use of power duct runs in our company is in the downtown areas of Davenport, Rock Island, and Moline. These areas have all the electrical facilities installed underground. These areas are designated as 120-208 volt secondary networks. The facilities that have been installed in these three networks areas at the present time are 838,798 duct feet of conduit. And we're talking about duct feet of conduit. That's the individual duct in the duct bank. 468 manholes, 110 handholds, and 47 transformer vaults. When we talk about the duct runs in the network area, we're really talking about a complete underground system, which consists of conduit, manholes, and transformer vaults, and also conduit that might rise above ground, and conduit that goes into the buildings themselves. The definition of the terms used in the layout of duct runs for underground transmission and distribution systems would be, first of all, a duct, which would be a pipe or tube designed or used for the accommodation of electric wire or cable. A service duct is a duct entering a consumer's premises for serving his electric load. A duct run would be a number of ducts joined together in a group. A manhole would be a chamber in which one or more duct runs terminate to give access to cables for splicing. A distribution manhole is a smaller manhole from which service ducts are run from the manhole to the buildings. In some cases, handholds have been used, and they're used in the aid of pulling cable. A transformer vault would be a concrete enclosure which would be large enough to house transformers and other associated equipment. The manhole frame and cover was made of cast iron casting set at ground level with a removable cover to allow entrance into a manhole. You might look at the network area of Davenport, which is outlined, and all this area in here is the area that's going to be, or most of it is now, served on the underground system. So that covers quite an area and quite a few blocks. We have also designated areas for Rock Island and Moline. This is pretty much typical, so. Some of the fundamental design features you might think about is to provide protection, housing, and access to cables, cable accessories, and related equipment. It also is to achieve minimum installation and operating costs. And the last would be to facilitate maintenance in order to reduce these costs to a minimum, consistent with a high service standard. The selection of manhole size and duct runs is the first thing to be done after it has been determined that the electrical circuits will be installed underground. The manhole size is determined by the formulas shown. I've got some sheets that I'll hand out here in a little bit, but we might so after you know the size of the cable that you're going to use, there's some formulas, and like I say, it is in the handout sheet. You can look at those later on, but it's essentially based on the length of the joint for splicing, and then with some given radius. In other words, the cable is entering here and leaving there, and so we need some radius to train the cable around to the wall for splicing, and also that allows for expansion and contraction in the cable due to heating and cooling cycles that it has. The number of conduit that we use in the duct run would be determined by the number of circuits to be installed, with spare conduit allotted for future circuits. In the networks, we pretty much got, in the majority of the cases, a standard configuration that try to use where possible. And if he's looking at a cross section through the conduit run, and this is concrete here, and that's the 18 4-inch conduit. The primary and secondary cables both go through these conduit runs, and as a rule we try to keep the primary cables on the outside ducts, and I think that will probably be explained to you later what the reason for that is. And also in the downtown areas, the city usually has use of one conduit for fire alarm or traffic control or whatever else they might want to use it for. The conduit size is determined by the cable that you're going to use, and it's based on the sum of the cross-sectional areas of the individual cables. It should not be more than the percentage of the internal cross-sectional area of the conduit. And there's some in other words, this gives you the percentage of conduit fill for cables that are not lead covered and cables that are lead covered. So if you had 3 cables lead covered, you could go to 40% of the conduit area. The standard size that we've been using in the network is 4-inch fiber conduit. Outside of the network areas at some of the substations and so forth, why we went to 4.5 and 5-inch. The fiber conduit is a mixture of waterproof bituminous insulating compound reinforced with an interwoven fibrous structure. Some of the other types that have been used, and the only place I know these are used in the network area, that we got some 3.5-inch square tile duct, and we don't use those anymore. They didn't work out too good for pulling cable. And we have used some plastic conduit and also some transite, which is asbestos cement. Might pass this piece of duct around. It's a little dirty, but time Brown gets through, it'll be cleaned off. Yeah, that is, some people are allergic to the fiber that comes off of that, so. Pretty much. The plastic duct, which is available, is a little easier to install. The lengths on that run about, you can get them in 20 and 30 foot lengths, where the fiber runs in 8 to 10 foot lengths, so there's fewer pieces to handle. But and the other thing is, on the pulling a cable, it does have a smoother bore, the fiber does, than what the plastic does, and it would aid somewhat in the pulling a cable. You are fighting friction all the time. The only difference is the cost on the plastic is somewhere around 4 to 5 cents a foot more than what the fiber is. The service duct would be a duct run that is run to the various buildings in the network areas, and the buildings are either served by a riser at the rear of the building or by a conduit that will enter the building through the basement wall. The riser usually serves or can serve several adjacent buildings, as long as the electrical service does not get too large in these buildings. And where the conduit enters the basement of a building, only that building is served from the duct run. In the case of large buildings, it's sometimes necessary to install a transformer vault either in or directly adjacent to the building. And we're in the process now of installing a vault in the new Damport Bank building addition in Damport. The transformer vaults, we've got them in various sizes, and when we first started out building them, we had they were designed to hold one transformer. The present design being used is for you to install 2 transformers per vault, unless it's some extra special place where we need more capacity, and we do have several of those, and then they're made larger to accommodate up to 4 transformers. That's the biggest we got so far. And the last one we put in was that took 4 transformers at the Modern Wooden Building in Rock Island. The vaults are usually located underneath the sidewalk area between the curb and the building line. And since in some cases the width of the sidewalk varies, and we can't get a standard transformer vault, which calls for 2 units to be placed side by side, so in some of these cases why it's necessary to lengthen out the vault and get the transformers at opposite ends. So essentially we have, if you're looking down at the top, we have a structure like this with a transformer setting there and a transformer setting there. Now that takes up about a little better than 11 feet, almost 12 in width across here. So if we get a sidewalk that is not wide enough for that, why then we might go to a longer narrow type, which has a transformer setting here with a bus room in here for terminating the secondary cables and another transformer setting over here. This one I was talking about at the Modern Woodman building, why it was it has 3 transformers in it now. And as the load grows there, why we can add the 4th at this point here. This being the bus room in between. You might look at a typical block section in the network area. Some of that didn't show too well, but anyway, this would be a street here, street over there, and one up here, with this being the alley in between. These cross-section areas, they represent the various buildings. This would represent our duct run going through the alley and up the streets. In the downtown area, Davenport, why the duct runs in the streets are in the north and south direction, and then the alleys in the east and west direction. This would be the larger manholes at the intersection of these 2 duct runs. Our transformer vault is located underneath the sidewalk at this point, with the duct run coming out to a manhole here. And the same thing is true on the other end. And these would be the distribution manholes in the alley to serve the various buildings. And this would be our service conduit, either a riser or conduit that's going directly into the basements of the building. Any questions so far? The next thing to be done is selection of the route and a complete survey of the area, locating the property lines, curb lines, and location of buildings. In addition, a profile of the ground line is necessary. We locate the water, sewer, and telephone manholes that can be seen from the surface. And we usually make contact with the city engineer and the city where the work is to be located, the telephone company, and our own gas department to obtain information on underground facilities they have in the area. A detailed drawing is then made showing all of the information gathered. The route of the duct run is then selected where we'll have the least conflict with the other utilities. If the construction is to be located in the street proper, we try to stay as close to the curb as possible to avoid street traffic, which we can't hardly block off all the streets in the downtown area. Out in, if we're out in an area where I got the substation and so forth, why we would try to go in the boulevard between the curb line and the property line. After this has been done, the layout of the system can now be made. Manholes are located at street and alley intersections, and in areas outside of the downtown areas, again talking about substations, the length between the manholes is determined by the allowable tension that can be placed on the electrical cable when it is pulled in the duct run. And this tension is calculated by the formula that's also in the handout sheets. I might just better start those around. Pass some of those. While they're talking about the pulling tension, this is sort of there's some sheets in there that shows what it is for a straight section too, but as you look through there, if we would take a conduit run that's, say, coming from a manhole at point A and going 300 feet to some point here and then rising up a pole as you go through there, you can see that if the cable reels would, if he was pulling the cable from point A to point D, the tension is considerably higher than if you were to be pulling the cable from point D to point A. And essentially the reason that it's better to pull from this point is you got the, in addition to the weight of the cable, which is helping to pull around this 90-degree bend. If we were pulling from point A, we got to pull this complete weight of this 300 feet of cable around that 90-degree bend, and it we've had some cases where that has got us into some trouble. The other thing that determines a manhole location would be a change in direction of the cable. In other words, if we were going down the street and made a 90-degree turn there, why we would, that's the reason for installing a manhole there, to get around these corners. The duct runs are terminated in the manholes with an end bell, and might take a look at one of those. Pass that around there. That's also made out of the same material as the conduit, so don't get it against your face. One of the reasons for using that end bell to terminate the conduit is to provide a rounded edge so that when you're pulling cable through the conduit and into the manhole, we don't have the possibility of damaging the lead jacket on the cable. Pulling eyes are installed in the manhole wall to provide a means for pulling cable. A sheave is usually attached to this eye, and the pulling cable that is used is run through this eye, through the duct run, through the eye, and then up to a winch on the truck. We also install ground rods in the floor of the manhole to be used for grounding the lead sheath of the cable, and also for grounding the neutral on 4-wire circuits. A sump hole is usually installed in the manhole floor, which can be used to pump the floor dry when somebody's going to do some work of some kind or other in the hole. This lets you pump the floor of the hole completely dry so that You don't have to stand in the water. The pumps we use will only pump with about that much water left if you don't have some pit for the pump to go into. The transformer vaults, which are located under the sidewalk at each, as a rule, at each street and alley intersection. In some locations, why they've been installed in the middle block, and this again depends on the buildings that we're trying to serve. If you go back again to the Davenport Bank building, where this particular one we're installing there is in the middle of the block, and due to the fact that it has a high electric use that it will have in the building. The vaults have 3 openings in the top slab of them, which is at sidewalk level, which one of them provides access for the transformer to be installed. And this opening is about 6 foot by 9 foot 7. And it's made up of 1 removable concrete slab and 2 removable grading slabs. We have a forced air opening, which is installed at one end of the vault, which in some cases we've used to install a shaft from this opening down to within a couple feet of the floor, and I've installed a fan there, and that's used for the cooling of the transformers. The third opening is used for access into the vault, and it's a hinge grating that has a lock on it, and then we have a permanent ladder installed in there to get from the sidewalk level to the floor. And on the vault floor we've got 2 concrete pads where the transformer is set on. A permanent sump pump is installed in the vault to keep the vault dry due to, well, in some places we've had, especially in Davenport, we have a heavy rain, why the catch basins don't handle the runoff water, and it overflows and through the grating into the vault. So, and also just from plain rainwater, why these pumps take care of that water. Although all the equipment in the vault is capable of operating completely submerged. The duct runs are laid out in a straight a line as possible, due to keep the pulling tension at a minimum. As can be seen by the bends, or what happens when you add bends to the duct runs. And as a rule, they should drain from one manhole to the other, either by sloping the duct run from one manhole to the other, or to have a high point in the middle and drain it both ways. All the duct runs are formed on the 2 sides when that concrete that we've seen before is poured around the ducts. The top of the envelope of the duct run is usually, we try to keep it around 2 feet below the street surface, and that was mainly done to keep somebody from running an air hammer through the paving slab and into our conduit runs. In cases where we've had to install duct runs underneath the railroad tracks, we pushed the casing, and the largest one that I know of is the one we had on Rock Island, which was about a 36-inch casing that we installed underneath the railroad tracks. And it was a length of about 60-some feet, I guess it was. The conduit then were bundled together, and we maintained about 1.5 inch spacing between conduit, and they were then pulled through the casing after the casing was installed. the ends were sealed off, and this whole casing end was pumped full of a grout. Which also got to be a little expensive. Where in that particular case there was, I think we had 9 or 12 conduit, I don't remember which it was, but one of the two. So it required that larger casing. And but the case where only 2 or 3 conduit are being installed under the tracks, or in some case where we've had to install conduit underneath the state highways, or under new paving where we couldn't break up the street and open trench the street to install the conduit, while we pushed well, first of all, we've augured a hole through there, which is about a 6 to 8 inch diameter hole, and then pulled a 4-inch steel conduit through this hole. The service ducts to the various buildings are usually installed so they'll drain towards the manholes, and this is so we don't drain water into the basements of buildings where we've installed conduit into the buildings. And where the duct run is to enter the basement of a building, it's necessary to obtain permission from the owner, so at least he knows what's going on. And in the case of a new building, arrangements are usually made with the architect who is handling the construction of the building to get our conduit installed through their basement wall. As a rule, the risers that we install, we try to locate those as close to the building electric service as possible, and that usually they have a weatherhead that comes out from their building, which is at the rear of the building at the alley line, and the conduit that we install in is usually directly below those. In the case where we might be going to an adjacent building, why the cable is then bracketed along the back of that building to the adjacent building. On these risers, why the concrete on the duct run is usually extended about a foot above the alley slab, and somewhere around a 10-foot length of galvanized steel conduit is then fastened to the building. The cable then comes up through that. The bends that are usually used in those are, on these risers, are 36-inch radius fiber bend. We made some tests some time ago due to the fact that we're having trouble pulling cable around these, and not in the network area, but these were at substations again. And we found that by changing from a fiber bend to a steel bend, why we cut down considerably on the amount of tension when we pull the cable through these ducts. So now all the riser poles at the substations, why we're installing 36-inch radius steel bends. Permits are also required for the duct run construction. In the case where we're going underneath railroad tracks, why we have to submit a sketch showing the location, the depth below the tracks where we're going to be, and then sometime 2 months later where we get a permit back saying it's okay to go ahead and do it. Where we're crossing or along state highways, that also requires a permit from the state, in which we submit construction drawings and they then grant us approval. We also need an excavation permit from the city when we're going through their streets. In the case of a transformer vault, it requires a building permit. In some cases where we get on private property for some reason or other, why we also need easements. Some of the construction practices that we use for manhole and duct run construction include having a contractor install the larger projects. And as a rule, we set time limits on the contractor for the different phases of the construction. We usually limit him to a one block section at a time. So in other words, if we're going 3 or 4 blocks, that he doesn't tear up the whole 3 or 4 blocks before completing the first block, which they like to do. Also, where it's necessary to cross the street with the duct run, the construction is usually done in 2 parts, so that we can maintain some kind of traffic flow, at least on one side of the street. Usually in the downtown areas, the street's wide enough that we can maintain traffic in each direction. The manholes are all, the ones we're building now anyway, are constructed of reinforced concrete. We have built some out of brick. That is, the sidewalls, the floor, and the top has always been out of concrete.
Poured or pre-formed? Poured or pre-formed?
The floor,
The sides.
the sides are formed. The concrete that we use around the duct run is a pea gravel mix, and since these conduit are spaced about 1.5 inches apart, the concrete flows real well around these conduit using this smaller pea gravel. The conduit runs are also reinforced, and that's done mainly when you're in the downtown areas. You never know who's going to be digging for sewer, water, or what have you, and they sometimes install their trenches underneath our duct run, and this way it does make sure that they're not going to fall in when they dig underneath them. On most of the jobs, we've tried to use a sand and clay mixture for backfilling, and the main reason for that was that instead of using pure sand, the sand tends to flow when somebody, in other words, if somebody was digging a trench alongside of ours at some future time, while all this sand usually flows out from where it had been placed. So by using the sand and clay mixture, we found that it pretty well stands in place, even though somebody does dig alongside of you. The street patches that have to be made after the conduit has been installed and backfilled, we usually in other words, we have a trench like so, and this is the street slab here. The city now makes us cut this back, and downport is running about 9 inches now. In other words, we have, after the conduit's been installed, we've backfilled up to this point, well, then we have to go in and break out this portion of the street on each side, so that the concrete patch that we put back in has a ledge to set on and doesn't have a tendency to settle. Like I say, this runs about 6 inches in downport, and then Moline has got to be about 3 feet now. So, in fact, in some place where we went down the alley, they make us replace the whole half of the alley, which is about 10 foot wide. Which, another thing that doesn't help any on the cost of these things when you try to install them, when you got to replace half of the downtown areas for them. Transformer vaults are usually also installed by contractors, and we set a time limit for the construction so that not to tie up the area any longer than is necessary. And the limit is usually set at 28 calendar days. Usually these areas are in front of, well, to begin with, we've got the sidewalk tied up, so it's necessary to construct a temporary walkway out in the street, and which is usually a wood frame with railings on the outside and usually enclosed on the sides. And I think the main reason for enclosing on the sides is in case in rain or snow cars going by won't splash water on the pedestrians that are using these walkways. In some cases these vaults are constructed in front of a doorway to various business places, so it's necessary to construct a bridge from the walkway over our excavated area so that people can still get in and out of these stores. Some of the construction costs and these various things, the manholes run, and depending on the size, from somewhere around $1,500 to $2,700 a piece. And on a two conduit duct run, that's two conduit in a duct bank. If we were under city streets, it's running somewhere around $18 a foot for the install. And if we're talking about that 18 conduit duct run, is around $46 a foot. And the transformer vault is running about $10,000. And that does not include the equipment that is installed in the transformer. That's just the basic structure itself. We got a few slides you might look at. Somebody will turn that projector on back there.
What was the cost in that larger 18 conduit per duct?
46.
46?
Just a second. Right. That shows some of the conduit stockpiled at a construction site. It's a little tough to see, but these are the couplings that are used. They're a plastic coupling, which is fairly flexible. We used to use a fiber coupling, which is made out of the same material as the conduit, but these conduit are always not perfectly round, and by using those fiber couplings, unless you painted the joints, why, there was a chance of the concrete seeping through these joints, because when you pour this concrete, it's usually fairly wet. And these plastic couplings pretty well conform to the conduit, even though they are maybe a little out of round. So they worked out a lot better. That's usually the typical equipment that's used for the excavations, which is a backhoe. This is some conduit installed out of Substation 38 in Rock Island. And this shows the conduit in place with the reinforcing rods that we're using. These conduit are set on what we call a base spacer, which gives you about roughly 3 inches of concrete underneath the conduit. This was one of those places where we was talking about where we augured a hole underneath the street. This happened to be a state highway up here, and as you can see, they started out on the other side. The hole was augured from the other side of the street over to here, and they started out about 3 foot apart. And these two came out pretty good, but this one wound up hugging the other one over there. And that's the one thing you run into when you auger underneath streets. Yeah, that's another view of the same thing. That shows them pouring the concrete around those conduit. The forms are in place there. there any questions so far?
Yes. Do you pick up any induced current in those blue rods?
No.
Allowing it close to them?
No, those are not looped all the way around. They're just a U-shaped bar that's around the conduit.
I was thinking ones particularly paralleling the individual duct.
No, I don't think so.
No problem.
We haven't any problem that I know of anyway. That's was one type of machine that was used for augering underneath the streets. This is a shaft for the auger. You can't see the auger; it's in the hole already, but it's a hollow shaft, and they use water running through the shaft and out to the end where the auger is, and that thing is just pushed through there by hand. But it works real well for what we were using it for. They start out with a 2-inch hole and run that through first, and when they get to the other end, then they hook on the larger size auger that they're going to use, and it cuts as you pull it back, so then you have the hole enlarged to a size that will let us get our 4-inch steel conduit through.
And do you get any concrete in that hole that's already under the street?
No, we didn't. We just let it run back as far as it'd go, and that was good.
That was steel conduit, though.
That was steel conduit underneath the street part. That shows the floor of one of the manholes. And this was that sump hole that we was talking about there a little bit ago. And this is a 10-foot ground rod that's been driven, which is about 4 to 6 inches above the floor then. As a rule, we install one of those in opposite corners of the manhole. And that shows some of the forms in place for the sidewalls.
Ken, doesn't the union contract have anything to do with the headroom in those manholes now? And the size, working space? Isn't that
Well,
determine the size of those now?
I think we've always had, at least in the ones we built in the last few years anyway, adequate headroom in those things.
Stand up with a hat on.
Didn't the union contract have something to do with that? I heard that something to that effect. The size of the manhole. The union contract had something. They wanted so much headroom, so much walking space.
Well, all I can say is I'm sure what we're building now has got adequate headroom in them. I'll grant you there's some in Damport that aren't too big. In fact, you can't even get into them, but then there's those handholds. At least the ones we're building now have adequate headroom in them, I'm sure. Unless you get somebody that's 8 foot tall or something like that. That shows some of the reinforcing in the top slab of the manhole. And this will be the hole that's left in there to get in and out of the hole. And that's a completed hole. This is in a boulevard, so all that was left showing was the manhole frame and cover. That's a view of a typical riser in the network areas. That's this being the alley surface with the concrete sticking about 6 to 9 inches, 9 inches to a foot above the alley, and this being the steel conduit going up the back of the building to the customer's weatherhead. That shows a typical riser out like at a substation. And that case, the concrete is usually run up a little higher, about 2 feet. And again, a 10-foot section of conduit installed on here, and that is fastened to the pole up on top. And I'm getting a little out of my territory, but anyway, that's the cables and coming out of these conduit are terminated at a point like so, and those are potheads, which we've got some examples which you can see a little later on. This shows this is an alley in Rock Island. It's been converted to the underground system, and it's pretty well free of any overhead wires. These again are some of the risers going up in the back of the buildings, and you can see this is a manhole here, and there's one down here, and those, they look close, but they're about 150 feet apart there. This building on the end has conduit that comes directly out of this manhole and goes into the basement of that building. This shows the top of one of our transformer walls. This is the opening for the transformers, this being the 2 grating panels with the removable concrete slab in between. Our forced air opening for ventilation is on at this point, and this would be the entrance to the vault.
So what's your grade?
That's 6 feet across there. 6 feet.
Well, I mean,
That opening? No, that's still that narrow size. It looks bigger on there. No, it isn't. We had a lot of trouble with this grating from time to time. The women walking over it would get their high heels caught in there, and I remember one over at Austin Crabs over here, which is now Citizens Federal Savings and Loan. I had a friend that worked there, and he used to tell me about all the women he used to have to go out and rescue out of the grating there because they had their heel caught. But I think that was kind of an excuse most of the time. But anyway, we've got this opening down now about as small as we can go and still have any room for ventilation for the transformers in there. I also threw these 2 in to show what some of the pulling operation of the cable. In other words, this being the three reels of cable. We have, in this case, it was a 4-wire circuit, the 3 phase cables, and this being the neutral cable over here. All 4 of those were pulled in the same duct. And this was just to show how they use these manholes after they're installed. And this is the manhole at the opposite end from where those reels were just set, or just on that previous slide. And it shows the winch cable being pulled out of that manhole. Yeah, I think we better leave it. Direct burial go, I think. I do have a few slides on that direct burial if anybody wants. We got enough time yet?
yeah, we go.
Due to this high cost of installing cables in conduit and manholes at the substations, we're trying a new method now, which is direct burying the 13 kV feeders. And this drawing shows a typical substation, this being the fenced area. And the thing we're talking about doing is reserving a 15-foot area around the substation to install these cables in. In other words, there won't be anything, no other structures or anything installed in this 15-foot area. It'll be reserved strictly for these direct burial cables. This is a piece of equipment that can be used for installing direct burial cables. This is a trencher. This shows an installation that we're making at Sub 75 in the west end of Davenport. This was again where they had to, even though this was direct burial, across the street we've got a steel conduit, galvanized steel conduit installed, and that's mainly in there for protection of the cable in case of somebody again doing work in the street. They at least will have something they can see before they get into our cable, we hope. That is the trench down there, and cable isn't in this one yet, but it does show the trenching they've done down through this area. And there's the cable laying in that trench. In this same job, they had to install a piece of conduit underneath this driveway. When we went to this direct burial cable in order to, and I'm getting out of my territory, but anyway, the current carrying capacity of the cable, if it's direct burial, is greater than it is if it's installed in conduit. So where we come out of the ground at the riser pole, in order to let this cable carry the same rating at this point as it does where it's buried directly in the ground, we've gone to a this is a U-guard that has a ventilator on the, in other words, this portion right here is installed in the ground and up to a point, and then this point is somewhat larger so that the air can circulate up through the part that's above the ground. I can see that a little better. And here is this space right in here is for ventilation, so that we have air can circulate up through that piece of U-guard. That's just another view of the same thing. And that shows the cables going out the top and up to the point where they'll terminate. Help somebody get the light there. I guess it's time for a break, so we'll be back at 6:30.